Okay, last time we had finished with an example of how to draw a full MO diagram. So there's one last caveat I want to give before we move on to talk about how we use a molecular orbital diagram. And that is, occasionally you get these weird molecules like a carbocation. So CH3 plus would be a carbocation. Turns out this is a really, really unstable carbocation, so this one doesn't actually exist, but we can still talk about it theoretically. Take a minute and try to draw yourself an MO diagram for a CH3 plus based on the steps that we followed last time. All right, so you should have started by looking at what MOs should exist in this molecule. And based on the structure, what MOs do you come up with? 3 sigma CHs. What else? Well, if you have sigma CHs, you also have to have sigma star, 3 sigma star CHs. Any lone pairs? Well, there's no lone pairs in it. The question is, are there orbitals, though? Well, let's think about it. We said to check if you have the right number of orbitals. Right now, we've listed 6 orbitals. There should be 4 from carbon and 1 from each hydrogen, so that would be a total of 7. So we're missing one. So there's one hidden orbital here that's not a lone pair, but doesn't seem to be part of any bond either. All right. Whenever you see a carbocation, the key is it's breaking the octet rule. So this is under an octet. And whenever you have something that's under an octet, that means there's going to be an empty non-bonding orbital on that atom. So that missing 7th orbital is going to be a non-bonding on carbon. To distinguish it from a lone pair, I'll usually include vacant after it, just because most of the time we think of those non-bonding orbitals as being lone pairs, but this one is an empty one. So this will be present anytime you have a carbocation or a boron atom that doesn't have a full octet. So the question is, what did I symbolize over there in the parentheses? For example, anytime you have a carbocation, so carbon with 3 bonds and a positive charge, doesn't matter what the 3 bonds are to. Same thing for boron. A boron with 3 bonds and no formal charge, doesn't matter what the 3 bonds are going to. There'll be a vacant orbital, and it's always actually going to be a p orbital, because if you think about the hybridization here, this carbon would be sp2 hybridized, and so there's going to be a p orbital left over. All right, so now you know basically all of the tricks of the trade for coming up with a complete MO diagram for a molecule. So now the question is, well, why would we bother doing that? Like, what is drawing all these lines on the page with the little arrow, like, what does that even do for me? So the reason is we can use these to predict reactions between molecules. We've already kind of used principles of just attraction between positive and negative parts of molecules to start predicting reactions. This will give us a little more precision with how to predict reactions and understand reactions. When you have interactions between filled molecular orbitals and empty molecular orbitals, that's when you can form new bonds. All right. Anytime you have a filled molecular orbital on one molecule and an empty molecular orbital on another molecule that can interact, those allow formation of new bonds. And I'm going to explain these sentences, but I think these are two good places to start. Filled MOs with relatively high energy are what we call good electron pair donors, meaning they're willing to go out and share those pairs of electrons. And when you have empty molecular orbitals with relatively low energy, they're what we would call good electron pair acceptors. So they're willing to be shared with. So we've talked before about pairs of electrons wanting to be shared. Those would be donor orbitals. And we've talked about atoms saying, okay, I'd love to share with you, but I need to make some space. Those would be the acceptor orbitals that are kind of responsible for those voice bubbles that we've drawn before. So on the next slide, I don't want you to actually try and draw this out at this point. But one way to think of this is if you have two reactants, molecule A and molecule B, when they come together, remember that orbitals on one can interact with orbitals on the other. And if we go back to the very beginning, we talked about these splitting diagrams where we said, you know, the two orbitals come together, they can overlap in phase and form a bonding orbital, overlap out of phase and form an antibonding orbital. The bonding orbital is lower in energy, the antibonding orbital is higher in energy. That works out well when you just have two electrons between the two orbitals you're talking about. Because then you fill in the lower energy orbital and the higher energy orbital remains empty. So the electrons get to go to a lower energy than they were before. So imagine you have two molecules interacting and each one has its own MO diagram. I've left off the labels here. Let's say the left is molecule A, the right is molecule B, and we want to consider interactions between two orbitals. So the first thing I would say is, well, what if two filled orbitals interact? So what if we consider the interaction between, you know, a filled orbital and a filled orbital down here? Like, what would happen if I took this orbital and this orbital that are both filled, and I said, okay, we're going to have those two interact. And I just draw a quick diagram of what that looks like. Well, when they come together, they're going to make a lower energy orbital and a higher energy orbital. But there's 4 electrons between the two of them. So I fill in the lower energy orbital, I fill in the higher energy orbital. So in this case, 2 electrons, these are happy because they're lower energy than they were before. Then we have 2 electrons that go in the higher energy one, those are sad. Okay? And so in this case, the happiness and the sadness cancel out. There's no net benefit to this interaction. So, the general statement we can make is interactions between 2 filled orbitals, they really are not helpful. All right? There's no net stabilization. We could also ask ourselves, all right, what happens if I have 2 empty orbitals interact? All right, so let's say I pick this orbital here and this orbital over here. Say, all right, what if I have those 2 orbitals interact? Well, I bring the 2 together. I make a lower energy orbital and a higher energy orbital. And if a tree falls in the woods and there's no electrons there to occupy the orbitals, does anyone care? No. Here there's no net stabilization because there's no electrons in either orbital. So in this case, there's no net stabilization. All right. So then what if we consider an interaction between an empty orbital on one molecule and a filled orbital on the other? So let's say I take this orbital and they interact. So this is molecule A, this is molecule B. I make a lower energy orbital, I make a higher energy orbital. There's 2 electrons to go in that lower energy orbital. How do they feel? Happy. There's no electrons in the empty orbital, so there's no one there to be sad. So we have 2 happy electrons, no sad electrons. Here there's going to be a net stabilization. So this is a net good interaction. So the moral of the story is what we care about when we're thinking about 2 molecules interacting with each other are interactions between filled orbitals on one and unfilled orbitals on the other. So these are the ones we focus on. Filled orbital interacting with an empty orbital. So that's the one takeaway. And it turns out that the closer in energy those 2 interacting orbitals are, the greater the net stabilization. All right? When we draw these little splitting diagrams, the closer in energy the two interacting orbitals start, the more the bonding orbital is stabilized from where it started. So if I were to consider the interaction between, say, so if there's a big energy difference, like you have your filled orbital here and your unfilled orbital way up here. Now when they interact, well, the filled orbital might gets stabilized a little bit. The unfilled orbital gets destabilized a little bit. But if you consider how much stabilization was there, and I drew it kind of crooked. But the point is, there's a very small stabilization. On the other hand, if I start with my filled orbital here and my unfilled orbital maybe just above it, that's when I'm going to get a relatively large stabilization from their interaction. So we're going to focus on interactions between filled and unfilled orbitals, and the most important ones are going to be the ones that are closest in energy. So I wouldn't, for instance, consider the interaction between, say, the bottom filled orbital on one and the top unfilled. If I consider that interaction between those two, it's really not going to have an effect because they're so different in energy. Effect. But if I consider the interaction between these two are close in energy, and so this will have a big effect. So what that means is I want my filled orbital to be high or low in energy. Am I going to consider high energy filled orbitals or low energy filled orbitals? High energy filled orbitals. And am I going to consider high energy or low energy empty orbitals? Low. All right. So going back to this statement I started with, filled molecular orbitals with relatively high energy are good donors. Empty molecular orbitals with relatively low energy are good acceptors. So those are going to be the best interactions between high energy donors and low energy acceptors because they'll be as close together as possible. All right, let's do an example. So take these two, try and sketch for yourself an MO diagram for the thing on the left, an MO diagram for the thing on the right, and then identify what donor you think will interact with what acceptor. All right, I drew my orbital or my lines to represent the orbitals. Help me name them. So for the SH minus, what's the lowest energy orbital? Sigma SH. Oh, except my stylus doesn't want to work. All right. And then next, non-bonding on S, my lone pairs, and then sigma star. All right, and I would have electrons in the lone pairs. All right. And then in CH3Cl, lowest energy orbital, sigma CCl, then sigma CH, then non-bonding on chlorine, sigma star CCl, and sigma star CH. I won't ask you to draw two MO diagrams next to each other and like get the relative energies right generally between the two because that's just complicated. But I tried to in my drawing here more or less get the relative energies between the two molecules about right. So sigma CCl is going to be lower energy than sigma SH, particularly because what kind of charge does the S have? Negative charge. And we talked yesterday about how a negative charge would make that atom less attractive, so that would increase the energy of those MOs. So sigma CH is going to be lower than sigma SH there. Sigma star CCl is going to be lower than sigma star SH. The lone pairs on chlorine are going to be lower energy than the lone pairs on sulfur. Yeah. Okay. So the question is now, what do you think is going to be the best donor orbital between these two, and what do you think is going to be the best acceptor orbital? Tongue? The sulfur lone pairs are going to be the best donors, yeah. The negative charge is kind of a tip-off. When you have an atom with a negative charge, usually its lone pairs are going to be very good donors. So these are going to be the best donor orbitals. All right, and who's going to be the best acceptor orbital? Sigma star CCl. This is going to be my best acceptor. All right. Question. So the question is, okay, how can those react? Well, let me explain. All right. I've identified what I think is going to donate and what I think is going to accept. Now the thing is, if the sulfur lone pair says, oh, I want to donate to sigma star CCl, first of all, what does sigma star CCl look like? It's going to have a lobe over here on the, it's going to have a lobe over here behind carbon. And it's going to have a lobe over here on the other side of chlorine. And something I pointed out, this was a while ago, it was before break, but a couple of lectures ago, for an antibonding orbital, has the bigger lobe on the less electronegative atom. All right. And then my sulfur lone pairs, these are just going to be sp3 hybridized orbitals. So, you know, there'd be one going this way, one going that way, one, you know, they'd be pointed out in different directions. So I have my lone pairs. So if one of the sulfur lone pairs decides to donate to sigma star CCl, what do you think happens when you put electrons into an antibonding orbital? Well, what does the word anti mean, or what does the prefix anti mean? Against. So what happens when you start putting electrons, donating electrons to an antibonding orbital? What do you think happens to the bond? It breaks. It breaks. So when these orbitals interact, When these orbitals interact, the sulfur lone pair says, hey, carbon, I would like to share this lone pair with you. Carbon says, sure, but I got to make space. So if you donate into this antibonding orbital, that's going to break the CCl bond and make the chloride fall off. And so, you know, I've shown you reactions kind of like this before. But my products are going to be CH3SH and chlorodyne. So by identifying the best donor and the best acceptor, we could then predict what was going to happen. And we'll be able to do that in a variety of cases. So we'll do more examples and we'll put more formal language to this coming up. But that's where we're headed. Question? The question is, why does the sulfur bond with carbon? Well, you know, there's a couple of ways to think about that. One is the antibonding orbital, the sigma star CCl orbital, is going to have a big part on carbon and only a small part on chlorine. And so there's going to be a better interaction between the lone pair and the part of the orbital, the part of the antibonding orbital that's on carbon. Also, just thinking in terms of electrostatic attraction, which we've done before. In CH3Cl, the carbon is partially positive, the chlorine is partially negative. So if the sulfur were to approach the chlorine, it would get repelled because the chlorine is negative and the sulfur is negative. So they wouldn't want to get near each other. Whereas if the sulfur attracts the carbon, just by electrostatic attraction, it's going to be attracted to carbon. And so it's more likely to react with that side. And that's going to be a general phenomenon. When one atom is donating to another molecule, it'll usually donate to the less electronegative atom. So the question is, if you're going to form a bond, don't the nodes have to line up? So over the course of the reaction, the orbitals will change. And we'll address that more next time. But the orbitals will be converted to brand new orbitals by the time the reaction's over. What we're looking at is really the interaction that's at the very beginning, that's there at the very beginning. So the question is the bond that accepts always going to break off? Well, if the acceptor orbital is an antibonding orbital, then you are always going to break that bond. Yes. So whenever the acceptor is an antibonding orbital, you will break the corresponding bond. All right. Great. I feel like we made great progress today, and we'll continue